C algebras are an important area of research in functional analysis, a branch of mathematics. A C** algebra is a complex algebra A of continuous linear operators on a complex Hilbert space with two additional properties. A is a topologically closed set in the norm topology of operators. A is closed under the operation of taking a joint of operators. C** algebras were first considered primarily for their use in quantum mechanics to model algebras of physical observables. This line of research began with Werner Heisenberg's matrix mechanics and in a more mathematically developed form with Pascual Jordan around 1933. Subsequently, John von Neumann attempted to establish a general framework for these algebras which culminated in a series of papers on rings of operators. These papers considered a special class of C** algebras which are now known as von Neumann algebras. Around 1943, the work of Israel Delphand and Mark Naimark yielded an abstract characterization of C** algebras making no reference to operators on a Hilbert space. C** algebras are now an important tool in the theory of unitary representations of locally compact groups, and are also used in algebraic formulations of quantum mechanics. Another active area of research is the program to obtain classification, or to determine the extent of which classification is possible, for separable simple nuclear C** algebras. Abstract characterization. We begin with the abstract characterization of C** algebras given in the 1943 paper by Gelfand and Naimark. A C** algebra A is a Banach algebra over the field of complex numbers, together with a map asterisk A. One writes x asterisk for the image of an element x of A. The map asterisk has the following properties. It is an involution for every x in A, for all x, y in A, for every complex number lambda in C and every x in A, for all x in A. Remark. The first three identities say that A is a * algebra. The last identity is called the C** identity and is equivalent to, which is sometimes called the B** identity. For history behind the name C** and B** algebras, see the history section below. The C** identity is a very strong requirement. For instance, together with the spectral radius formula, it implies that the C** norm is uniquely determined by the algebraic structure, a bounded linear map, pi, a B, between C** algebras A and B is called a * homomorphism if for x and y in A, for x in A. In the case of C** algebras, any * homomorphism pi between C** algebras is non-expansive, i.e., bounded with norm 1. Furthermore, an injective * homomorphism between C** algebras is isometric. These are consequences of the C** identity. A bijective * homomorphism pi is called a C** isomorphism, in which case A and B are said to be isomorphic. Some history. B** algebras and C** algebras. The term B** algebra was introduced by C. E. Rickart in 1946 to describe Banach algebras that satisfy the condition for all x in the given B** algebra. This condition automatically implies that the asterisk involution is isometric, that is, x equals x asterisk. Hence, x equals x asterisk, and therefore, a B** algebra is also a C** algebra. Conversely, the C** condition implies the B** condition. This is non-trivial, and can be proved without using the condition x equals x asterisk. For these reasons, the term B** algebra is rarely used in current terminology, and has been replaced by the term C** algebra. The term C*algebra was introduced by I. E. Siegel in 1947 to describe norm-closed subalgebras of B, namely, the space of bounded operators on some Hilbert space H. C stood for closed. In his paper, Siegel defines a C*algebra as a uniformly closed, self-adjoint algebra of bounded operators on a Hilbert space. Structure of C*algebras. C*algebras have a large number of properties that are technically convenient. Some of these properties can be established by using the continuous functional calculus or by reduction to commutative C*algebras. In the latter case, we can use the fact that the structure of these is completely determined by the Gelfand isomorphism. Self-adjoint elements are those of the form x equals x asterisk. The set of elements of a C*algebra A of the form x asterisk x forms a closed convex cone. This cone is identical to the elements of the form x asterisk. Elements of this cone are called non-negative. The set of self-adjoint elements of a C*algebra A naturally has the structure of a partially ordered vector space. The ordering is usually denoted. In this ordering, a self-adjoint element x of A satisfies x0 if and only if the spectrum of x is non-negative, if and only if x equals s asterisk s for some s. Two self-adjoint elements x and y of A satisfy xy if x minus y0. This partially ordered subspace allows the definition of a positive linear functional on a C*algebra, which in turn is used to define the states of a C*algebra, which in turn can be used to construct the spectrum of a C*algebra using the GNS construction. Quotients and approximate identities. Any C*algebra A has an approximate identity. In fact, there is a directed family, E lambda I of self-adjoint elements of A such that in case A is separable, A has a sequential approximate identity. More generally, A will have a sequential approximate identity if and only if A contains a strictly positive element, i.e., a positive element H such that H is dense in A. Using approximate identities, one can show that the algebraic quotient of a C*algebra by a closed proper two-sided ideal, with the natural norm, is a C*algebra. Similarly, a closed two-sided ideal of a C*algebra is itself a C*algebra. Examples: finite-dimensional C*algebras. The algebra M of n times n matrices over C becomes a C*algebra if we consider matrices as operators on the Euclidean space Cn, and use the operator norm on matrices. The involution is given by the conjugate transpose. More generally, one can consider finite direct sums of matrix algebras. In fact, all C*algebras that are finite-dimensional as vector spaces are of this form, up to isomorphism. The self-adjoint requirement means finite-dimensional C*algebras are semi-simple, from which fact one can deduce the following theorem of Artin-Wedderburn type. Theorem: a finite-dimensional C*algebra A is canonically isomorphic to a finite direct sum where min A is the set of minimal non-zero self-adjoint central projections of A. Each C*algebra A is isomorphic to the full matrix algebra M. C. The finite family indexed on min A given by dim E is called the dimension vector of A. This vector uniquely determines the isomorphism class of the finite-dimensional C*algebra. In the language of K-theory, this vector is the positive cone of the K0 group of A. An immediate generalization of finite-dimensional C*algebras are the approximately finite-dimensional C*algebras. C*algebras of operators. The prototypical example of a C*algebra is the algebra B of bounded linear operators defined on a complex Hilbert space H. Here x asterisk denotes the adjoint operator of the operator x. HH. In fact, every C*algebra A is asterisk isomorphic to a norm-closed adjoint closed subalgebra of B for a suitable Hilbert space. H. This is the content of the Gelfand-Naimark theorem. C** algebras of compact operators. Let H be a separable infinite-dimensional Hilbert space. The algebra K of compact operators on H is a norm-closed subalgebra of B. It is also closed under involution, hence it is a C** algebra. Concrete C** algebras of compact operators admit a characterization similar to Wedderburn's theorem for finite-dimensional C** algebras. Theorem: if A is a C** subalgebra of K, then there exists Hilbert spaces I such that where the direct sum consists of elements of the Cartesian product pi k with T, 0, though K does not have an identity element, a sequential approximate identity for K can be developed. To be specific, H is isomorphic to the space of square-summable sequences L2. We may assume that H equals L2. For each natural number n, let Hn be the subspace of sequences of L2 which vanish for indices Kn, and let n be the orthogonal projection onto Hn. The sequence N is an approximate identity for K. K is a two-sided closed ideal of B. For separable Hilbert spaces, it is the unique ideal. The quotient of B by K is the Calkin algebra. Commutative C** algebras. Let X be a locally compact Hausdorff space. The space of complex-valued continuous functions on X that vanish at infinity form a commutative C** algebra under pointwise multiplication and addition. The involution is pointwise conjugation. Has a multiplicative unit element if and only if is compact, as does any C** algebra. Has an approximate identity. In the case of this is immediate. Consider the directed set of compact subsets of, and for each compact let be a function of compact support which is identically 1 on. Such functions exist by the TS or extension theorem which applies to locally compact Hausdorff spaces. Function sequence is an approximate identity. The Gelfand representation states that every commutative C** algebra is isomorphic to the algebra, whereas the space of characters equipped with the weak topology. Furthermore, if is isomorphic to as a C** algebras, it follows that an are homeomorphic. This characterization is one of the motivations for the non-commutative topology and non-commutative geometry programs. C** enveloping algebra. Given a Banach algebra A with an approximate identity, there is a unique C** algebra E an morphism pi from A into E which is universal, that is, every other continuous morphism pi, a B factors uniquely through pi. The algebra E is called the C** enveloping algebra of the Banach algebra A. Of particular importance is the C** algebra of a locally compact group G. This is defined as the enveloping C** algebra of the group algebra of G. The C** algebra of G provides context for general harmonic analysis of G in the case G is non-abelian. In particular, the dual of a locally compact group is defined to be the primitive ideal space of the group C** algebra. See spectrum of a C** algebra. Von Neumann algebras. Von Neumann algebras, known as W** algebras before the 1960s, are a special kind of C** algebra. They are required to be closed in the weak operator topology, which is weaker than the norm topology. The Sherman-Takeda theorem implies that any C** algebra has a universal enveloping W** algebra, such that any homomorphism to a W** algebra factors through it. Type for C** algebras. A C** algebra A is of type 1 if and only if for all non-degenerate representations pi of A. The von Neumann algebra pi is a type 1 von Neumann algebra. In fact, it is sufficient to consider only factor representations, i.e., representations pi for which pi is a factor. A locally compact group is said to be of type 1 if and only if its group C** algebra is type 1. However, if a C** algebra has non-type 1 representations, then by results the James-Glimmett also has representations of type 2 and type 3. Thus for C** algebras and locally compact groups, it is only meaningful to speak of type 1 and non-type 1 properties. C** algebras and quantum field theory. In quantum mechanics, one typically describes a physical system with a C** algebra A with unit element. The self-adjoint elements of A are thought of as the observables, the measurable quantities, of the system. A state of the system is defined as a positive functional on A0 for all UA, such that phi equals 1. The expected value of the observable x, if the system is in state phi, is then phi. This C** algebra approach is used in the Hart-Cassler axiomatization of local quantum field theory, where every open set of Minkowski spacetime is associated with a C** algebra.